Welcome back. In this video, I'll run through a proof of Theorem 1.8. It says that the size of every bipartite graph of order n is at most the floor of n squared over 4. So again, make sure you understand what a bipartite graph is before proceeding with this video, because that'll be necessary, right? This concerns bipartite graphs, so we need to know what that is. And in particular, the maximum here at most n squared over 4, we can get away. There are bipartite graphs with at most, or with exactly n squared over 4 floor edges. So this occurs when we divide our vertex set into two as equal as we can get them sets, and then join all the vertices between those sets with edges. So the idea here is if I had a set of vertices of order 5, so if n is 5, I have these 5 vertices. What I'll do is I'll split them as best I can in half, so roughly in half. In that case, and what I mean by as best I can is I'll make one of the partite sets n over 2 ceiling, and one of the partite sets n over 2 floor. So in the case when n is odd, there'll be a little bit of discrepancy in size. They'll just be off by 1. If n is even, they'll both be equal sized. The partite sets, that is. And then what I'll do is I'll make a complete bipartite graph out of this. I'll form the graph K n over 2 floor, n over 2 ceiling. So a balanced complete bipartite graph. And I'll join, so what that means is I'll join all the vertices between partite sets. I'll put edges between vertices in the partite set. And so here when n was 5, we can count m is 2 times 3 over 2. Oh, sorry, not 2 times 3 over 2, but 2 times 3. M is 6 here. And so in this case, n squared over 4, let's check, n squared is 25 divided by 4. So this is, 24 over 4 is 6, so this is 6.25, so take the floor of that, this is 6. And that's exactly what my m is. And so this will be the case if n is even. Again, this will be split exactly in the middle, and I'll achieve exactly n squared over 4. In the case when n is odd, I'll get the floor of n squared over 4. So we can achieve this, but what this theorem is saying is that we can't do any better. We can't stuff any more edges. This is sort of the best case scenario in terms of getting the most edges into a bipartite graph. So how do we prove this? I'll say proof sketch. I'll sort of run through the proof of this one. The idea is we're gonna follow the same sort of pattern here. We're gonna split our vertices into 2 sets to form a bipartite graph. But we're gonna do this in general with a variable number of vertices in each partite set. We'll count the edges and we'll see that it can never be more than the floor of n squared over 4. So how does this work? So we have a graph G of order n, and I'll let U, so I'm going to partition the vertices into 2 sets. I'll let U and W be the partite sets. And there's lots of different options for how I could split these up. And I'll just focus on how many are in each one. So I'll assume there are x vertices in U. So I'll take some x number of vertices of G and put them in the partite set U. And then whatever left over, I'll put that in W. So that would be n minus x vertices in W. For some 1 less than or equal to x less than or equal to n minus 1. You might wonder why we don't include 0 here for x. It's possible I don't put any vertices into U, but in that case, there wouldn't be any edges at all in the graph. We would have the empty graph, which has size 0, And so that's, right, that doesn't achieve the maximum. That's not more than n squared over 4, so we don't have to worry about that. And what I'll do here is I'll count the number of edges in this graph. Let me maybe draw a picture. So I have u, I've taken these x vertices, x many here, and w, whatever is left over. So n minus x vertices here. And the most number of edges that could be in a graph like this, if this is my partite sets, would be if I joined up, if I gave all the edges in between, or created all these edges in between. That'll be sort of the upper bound on this. And so how many edges would be in that graph? So let's see. So the size of G, it can't be any more than this construction. This is the most number of edges I can put into this construction is, well, let's call it M. It's M. And so let's see. What would be M? So M would be if I just count up all the edges incident with U. And so that would be M would be, there are x many vertices in U times the degree of each vertex, n minus x. So M, the size of G, is x times n minus x here. And we're going to do a little bit of clever stuff here, messing with inequalities. So what we'll do is we're going to start with, and this might look like it comes out of nowhere, and it kind of does. This is what happens when you play around with the problem for a while. You find an elegant way of doing it. When you go back to write the proof for it, it seems like things kind of come out of nowhere, but the logic still tracks. And so if this seems like it's out of nowhere, it kind of is. So I'll say notice, we're just going to take this quantity, n minus 2x, and if we square that, so n minus 2x, it could be negative, could be positive, could be 0. But no matter what, if I square this thing, even if it's negative, it'll be greater than or equal to 0. And so if I expand this out, this means what? N squared minus 4nx plus 4x squared is greater than or equal to 0. Rewriting that, this tells me n squared is greater than or equal to 4nx minus 4x squared. And I can simplify this a bit. I can pull a 4x out of everything, in particular 4x times, what am I left with? N minus x. So look, I have x times n minus x, that's m, so this is 4m. So n squared has to be greater than or equal to 4m. Rewriting this, I get n squared over 4 has to be greater than or equal to m. M less than or equal to n squared over 4. And lastly, since m has to be an integer, I can certainly say it's less than or equal to n squared over 4, but I can say more. Since m is an integer, I get to round this down. If n squared over 4 is an integer, it's fine. M will still be less than or equal to the floor of this. I won't round it down. But if this is a half or a quarter, something like that, has some is not an integer, I can round that down since I know that m is an integer. So m is less than or equal to the floor of n squared over 4. And that's all for this one. It's just a little clever inequality, playing around with inequalities, and eventually it comes out that m is less than or equal to this.